your favorite gardener, physician, and weatherman. They can all make important contributions to the health of that superorganism on which we all depend, planet Earth. It's planetary medicine, this time on Science Without Walls. You've already met a few of my heroines and heroes. Here's another one. James Lovelock has been credited by major science and medical writers as having produced, quote, one of the major discontinuities in human thought, the view of the Earth as a coherent system of life, self-regulating, sort of an immense organism, unquote. James Lovelock is a somewhat isolated, controversial, non-traditional inventor and scientific genius who has encouraged many people to change their views and perception of planet Earth. For the last several decades, Lovelock has been an independent scientist, engineer, and inventor, not tied to any institution, to any government agency, or to any company. He has had success as an inventor, which allows him an income to pursue his scientific interests in his own home laboratory in southwestern England. He is a true inter- and multidisciplinarian who looks at planet Earth from the widest possible perspective. Lovelock is not a geologist, he's not an oceanographer, he's not an atmospheric scientist, he's not a microbiologist, he's not a physician. He's neither a chemist, physicist, nor biologist. He is all of these, and he utilizes all of these disciplines to focus on the nature and the behavior of planet Earth. He is the world's first planetary physician. We discussed earlier how life might have evolved on Earth, and we took the existence of Earth as a given. The Earth formed nearly 5 billion years ago. Life was constrained to evolve given the conditions, the elements, chemicals, and temperatures of planet Earth. We now know that bacteria evolved with the abilities to collect the sun's photons and to use the energy collected together with carbon dioxide to produce oxygen, chemicals, and, of course, more bacteria. Their photosynthesis was so successful that these bacteria, together with photosynthetic protists, brought down the carbon dioxide level and greatly increased the oxygen level, permitting large respiration-based organisms, like you and me, to evolve, live, and prosper. So there's no question that life on Earth has modified the Earth itself. Life has made it green. Photosynthetic life has decreased CO2 and increased oxygen. And animal life does just the opposite, producing a wonderful balance. That's all been known and appreciated for a long time. But Lovelock says this is just part of the story. He believes that life and the planet it inhabits have a variety of mechanisms for regulation of the temperature and composition of that planet. He argues that there's a balance between the inorganic part of the planet and the organic or living part. He says that Earth is a superorganism. He, of course, doesn't really believe that Earth is alive in the sense that you and I are. Earth doesn't reproduce. There are no long strings of Earth DNA. He calls his idea the Gaia hypothesis, named after the Greek goddess of the Earth.
It's just the whole planet's alive. And I've chosen to give that notion the title, the Gaia hypothesis, and I've chosen the word Gaia because that's what the ancient Greeks called Mother Earth.
He has developed the Gaia hypothesis to encourage all of us to take a broader view of our activities here on planet Earth, to induce us to get above our narrow, discipline-focused, myopic views and look at Earth and the life on it as a large system. Earth is a somewhat isolated system in this particular solar system, receiving energy from the sun and radiating some of that energy back into space. Every now and then we accept matter in the form of meteors and throw some matter out in the form of space probes, like Voyager and Galileo. But basically, we are a materially closed system, meaning no matter is exchanged. And we are an energy open system. We do indeed exchange energy through our atmosphere. An example of a fully sealed closed system is a sealed can of fruit or vegetables. You are an example of an open system, exchanging both energy and matter with your surroundings. So let's assume that perhaps 30 years from now, your daughter comes back on that starship, the one in our last program, and reanalyzes planet Earth. Assuming business as usual between now and then, and assuming that her instruments are more sensitive, she will discover that the dominant life form on the planet was not metallic automobiles, but rather those little organic things that inhabit and control them, humans. But now there are not 5 billion of them on the planet. There are over 10 billion. Most of the green has been eliminated. Earth's average temperature has increased because the CO2 level has continued to increase significantly, further increasing the greenhouse effect. These 10 billion organisms seem to be constantly enmeshed in wars related to food, water, and land. If you look at the Earth from the perspective of a planetary physician, you might conclude, already in the last program, that Earth was a sick planet. Your daughter might well conclude, visiting 30 years from now, if nothing was done in the meantime, that Earth is terminally ill, that it may indeed be in the process of transformation to a dead, lifeless planet like Mars. This is all part of Lovelock's message. He intentionally overstates the case to draw attention to the problems of the present. We are all so immersed in our oversized, overstuffed day planners, so involved in our own duties and responsibilities, schedules and commitments, and constantly bombarded by a barrage of ads, bells, buzzers, programs, screams, cries, and telephone calls. It's difficult for anyone to get our attention. We have so many transient epicenters constantly forming in our consciousness that we have trouble allowing any one of them to grow to the point where we can focus, concentrate, or think. We're so worried, including here in Utah, about kids with attention deficit disorder. But we have a national attention deficit disorder epidemic. We all have far too many transient epicenters and little real thought. And that is attention deficit disorder. So Lovelock has had to ring the bell very loudly and very often. He and others like him, including Carl Sagan and Lynn Margulis, are trying hard to get our collective attention, to encourage some planetary diagnosis and some planetary medicine. A physician treats a patient by first making a diagnosis of what's wrong. She tries to learn the patient's pathology. Physicians try to figure out the reason for that pathology and then try to eliminate whatever it was that caused that pathology. That's the treatment phase. So the first stage in serving as a planetary physician is to determine or to define what is health. What is a healthy planet? Lovelock argues that for 1 billion years, life and the rest of the planet have been in balance, maintaining an oxygen concentration of about 21% and a CO2 concentration of about 0.03%, and an average surface temperature of about 13 degrees centigrade. That's the normal temperature of the planet. We can measure your temperature with a thermometer and measure the gases in the air you inhale and exhale, determining if there is any significant disturbance in the amount of oxygen you take in or the amount of CO2 you released. If your lungs are very inefficient in taking in oxygen, or your hemoglobin is very inefficient or ineffective in binding or releasing it, or if your respiratory system is inadequately removing carbon dioxide, you would have some sort of respiratory distress. This would result in biochemical changes, which would alter your overall metabolism. You would indeed be very sick. Well, Lovelock argues that Earth's temperature and respiration, its atmospheric gases, have been roughly constant for 1 billion years, and that's what we should define as health. If it seems to be significantly changing, particularly over a very short period of time, you might say that the planet is ill and may get sicker unless there is some kind of medical, planetary intervention. Lovelock begins his study of planetary medicine much as you'd begin the study of medicine if you were a medical student. Medical school involves 6 key subjects: anatomy, physiology, biochemistry. These 3 tell you how you function. Pathology deals with what goes wrong. Diagnosis tells what is wrong. And medicine is the fix-it or treatment part. Lovelock considers the anatomy of the planet, its atmosphere, its land masses, its ocean masses. The exchange of the gases in the atmosphere is Earth's respiratory system. The movement of the waters of the planet, condensation, rain, snow, rivers, is its circulatory system. He considers the major ecosystems of the planet as analogous to organs. For example, the rainforest could be considered an enormous photosynthetic organ. The land area with high animal populations could be considered another organ. All of these ecosystems, these various organs, are linked to each other. All, of course, are components of planet Earth and subsystems of Gaia. He then considers the physiology of Earth, the feedback loops, how things are regulated, and compares that to the regulatory and feedback mechanisms in your own physiology. How is your temperature regulated? How is your blood oxygen content regulated? He looks at the lifespan of the planet. It's already about 5 billion years old. It may have another 5 billion years to go before its energy input, the sun, begins to significantly change. Earth is already middle-aged in a planetary sense. You and I have a life expectancy of about 75 years. We expect things to change, to deteriorate as we approach the end of that life expectancy, but we expect our health to be relatively stable until we begin to reach old age. If your health changes abruptly in the next few hours or the next few weeks, you suspect something is wrong, and you'd see your physician. Lovelock also examines planetary biochemistry. He looks at the carbon dioxide cycle and realizes that it's not just plants consuming CO2 and animals producing it. Life has evolved ways of binding carbon dioxide in minerals and releasing it from those minerals. We have many inorganic materials which contain carbon dioxide, such as various calcium carbonates. Much of our calcium carbonate, our limestone, is not inorganic. It's organic in the sense that it was actually produced by living organisms. Organisms which make beautiful calcium carbonate shells, corals, mollusks, and many plankton. Much of the limestone and chalk on our planet would not be there, at least not in that form, were it not for the life which secreted and deposited it. Lovelock notes a very close coupling between the organic and the inorganic. In fact, there are now emerging scientific disciplines, new disciplines, that go by the names of biogeology, geochemistry, geobiology, and even biogeochemistry. Lovelock looks at the relationships between oxygen, methane, and carbon dioxide. The annual flux or flow of oxygen and carbon dioxide are each in the range of 100 to 200 billion tons. That's about 10 to the 14th kilograms per year. Enormous numbers, meaning that our atmosphere has achieved a very dynamic equilibrium. The major components to this global carbon cycle are photosynthesis and respiration. Lovelock says oxygen concentration is tightly regulated, possibly because of the effect of oxygen concentration on chemical oxidation, on combustion. Below 10% oxygen, burning is difficult, and above 25%, combustion is intense. The organic matter on the surface of the planet would literally have combusted away. So oxygen has been approximately stable at 20 to 21% for of the order of 1 billion years. Lovelock has looked at the sulfur balance, an area which has not been extensively studied, concluding that the oceans and their marine algae play a key role in the nucleation of clouds through sulfur-containing aerosols produced by those marine algae. Lovelock and others have also examined the nitrogen cycle and the flux of all other major atmospheric gases. Just as a physiologist and physician would look at your metabolic fluxes in trying to assess or diagnose metabolic or physiologic problems. You regulate your temperature, your pH, the number and type of ions in your physiologic fluids, to maintain the conditions which your biochemistry and your metabolism require. If your pH changes by just a few tenths of a pH unit, if your temperature changes by just several degrees, if the ionic makeup of your blood changes even slightly, you are very ill. You must maintain relative constancy in these chemical and physical parameters. You maintain an active homeostasis, meaning you continually regulate your internal environment to keep it relatively constant. Lovelock claims that that's exactly what the planet does, that the life forms on the planet, in an unintentional, undirected, non-DNA controlled way, essentially regulate the planet's atmosphere and temperature. As atmospheric gas concentrations change, the amount of solar radiation hitting the surface of the planet changes, the temperature changes. CO2 and solar flux go up, and perhaps green plants increase, consuming CO2, producing oxygen. Animals consume oxygen and produce CO2, and, through man's actions, burn incredible amounts of organic matter, producing heat and CO2 in a variety of processes. Cattle and other large herds, domesticated and managed by man, produce large amounts of methane. There are other means by which CO2 concentration is controlled, such as the equilibrium between carbonates in rocks and minerals and the CO2 in the air. All of these processes interact and regulate each other as an extremely complex system with very large numbers of feedbacks. It's all worked to maintain a relatively constant environment for nearly 1 billion years, until 100 or so years ago. It used to be that it took thousands, tens of thousands, even millions and tens of millions of years to produce significant changes. But it's now clear that humans in the last 100 years have produced major changes. Although the planet may indeed be somewhat self-regulating, its regulatory processes take time, hundreds of millions of years to adjust. The massive changes that mankind has made are instantaneous in terms of Gaia's planetary metabolism. Earth's systems are unable to respond fast enough to prevent major biological crises. So Lovelock concludes that Gaia, that planet Earth, has a significant fever. We call the fever the greenhouse effect. All studies show that her fever will increase significantly over the next 10 to 20 years and beyond. Lovelock fears that the increased fever and the increased pollutants and toxins the continued burning of fossil fuels, and other human activities are leading to even more serious pathologies for planet Earth. James Lovelock is a remarkable man. He first began to appreciate the complexity and delicateness of Earth in the 1960s when he was a consultant for NASA, helping them to design instruments and experiments for the detection of life on other worlds. He says, "For me, the personal revelation of Gaia came quite suddenly, like a flash of enlightenment." He did the thought experiment you did in the last program. By approaching our planet from afar, could we tell anything about life on that planet from the composition of its atmosphere? He concluded that we certainly can. He understood that if life were indeed strong and widespread throughout the planet, life's actions and activities would have some measurable effect on the atmosphere of that planet. By comparing the atmospheres of the various planets in the solar system with that of Earth, he concluded that the other planets are lifeless, that Earth appears to be unique. Lovelock further concluded that the Earth's atmosphere is a very unusual and unstable mixture of gases, that there is no way these gases could be in static equilibrium. There had to be continual production and replenishment. Otherwise, the gases would chemically react with one another and produce an equilibrium, a static composition, similar to that of Mars or Venus. The only way the concentrations of the reactive gases, oxygen and methane, could be maintained is if they were being actively produced on the surface of the planet, produced by life. Almost no one argues anymore that the presence of life on Earth actually has and continues to influence the composition and properties of its atmosphere. And almost no one argues anymore that man's activities in the last 100 years have significantly altered the nature of that atmosphere and the composition of the oceans. The question today deals with the magnitude, the significance of those changes, today and over the next 10 to 20 years. It is very clear, however, that if our population continues to exponentially increase, as dramatically as it has in the last 50 or so years, and if that increasing population continues to expect an energy-intensive and materials-intensive quality of life or standard of living, then the Earth's atmosphere, its oceans, its soils, and other waters will continue to dramatically deteriorate. It's unlikely that man will be able to technologically accommodate to such dramatic changes. Your children and grandchildren will fully experience the negative outcomes of these trends. This is why so many folks are worried about the population problem, or what has even been called the population bomb. So the next time you feel a bit ill or feverish, or someone in your family gets sick, and you're lying there with a thermometer in your mouth, possibly sick in bed, waiting for the flu to subside, try to lean back. Let those transient epicenters in your brain expand and develop, and deliberate on that beautiful blue, green, red, and white ball. Deliberate on its health and viability. After all, no matter how technologically advanced man may become, no matter how many planets or even solar systems we may eventually explore, and possibly even populate, this will always be the home planet, our pale blue dot. It would be a real tragedy for your progeny 20, 50, or 200 years from now to come back to trace their genealogy and find the Earth lifeless and dead. That's why you see bumper stickers and posters that read, "Think globally, act locally," "Respect your mother, Mother Earth that is," "You are here," and "Extinction is forever." Senator Jake Garn expresses it better than I can.
What do you carry with you from those, I believe, 7 days in orbit 7 years later?
First of all, an intense frustration at the inability to describe how magnificently beautiful this Earth is from space. And it really is impossible to describe how magnificent it is to go into a sunset period and see the sun refract through the Earth's atmosphere and produce a rainbow all the way around the edge of the Earth.
They paved paradise, put up a parking lot with a pink hotel, a boutique, and a swinging hot spot. Don't it always seem to go that you don't know what you've got till it's gone? They paved paradise, put up a parking lot. They took all the trees, put them in a tree museum, and they charged the people $1.50 just to see them. Seem to go that you don't know what you've got till it's gone. They paved paradise, put up a parking lot. Hey, farmer, farmer, put away the DDT now. Give me spots on my apples, or leave me the birds and the bees. Please don't it always seem to go that you don't know what you've got till it's gone. They paved paradise, put up a parking lot. Late last night, I heard the screen door slam, and a big yellow taxi took away my old man. Don't it always seem to go that you don't know what you've got till it's gone? They paved paradise, put up a parking lot. I said, don't it always seem to go that you don't know what you've got till it's gone? They paved paradise, put up a parking lot. They paved paradise, put up a parking lot. They paved paradise, put up a parking lot.